Hi, as a conclusion for our first buck converter design, we are going to evaluate the contribution of each component in terms of power losses and in terms of size. So as we always do, here you have the simulation scheme that we use in our design. We have introduced this schematic a lot of times before, so feel free to reproduce it. And let's start with the power losses. From previous videos, we know that the total power losses we have according to LTspice is 6.6 watts. So let's see the contribution of each device. Here we have power losses, and I will indicate here the contribution of each component. Let's start with the MOSFET. I have split the MOSFET contribution into two parts: conduction losses and switching losses. In terms of conduction, we have 0.2 watts, so it's a very small contribution. And then in terms of switching, we have 0.4, a higher quantity, but it's not very important considering the overall value. It's important to note that here in the part of switching, I have included turn on losses and turn off losses. In summary, total power losses we have on the MOSFET is 0.6. So, well, it's not negligible, but it's a small part of total value. Then we have the diode. Remember that in the diode, we focus on the conduction because we consider that switching losses on the diode are negligible. And in this case, the value that we obtained was 4.7 watts. This is the main contribution to the final value. So this is something that we will try to improve in future designs. And finally, we have the inductor, whose contribution is 1.3. It's true that we don't have a video analyzing this, but this is because this analysis is very straightforward, taking into account previous methods, okay, or the methods that we have introduced in previous videos. Basically, because our model is very simple, we only have the ideal inductance in series with the equivalent resistance of the windings. So we only consume power in that resistance. It's very easy to evaluate the power consumption in that resistor in LTspice. So the final value is 1.3. It's true that in a real prototype, the contribution of this inductor is higher, because remember that, as we explained, the datasheet of that inductor doesn't include information about the core, so we cannot evaluate, for instance, core losses. In any case, the conclusion here is the main contribution for the total power losses comes from the diode. So as I say, we will try to improve it in future designs. Let's talk about the size. So here you have the total size. In this case, we evaluate the size in a simple way by summing the size of each component. It's not a very real value. It's not what we will have in a real prototype, because in the prototype you have to put the components in the PCB, but it's a fair comparison in order to evaluate future design. So, well, it's what we can do at this point. So here you have the total size as a reference. As I say, is the sum of the individual components, and let's see the contribution of each one. So first of all, we have the MOSFET. The contribution is negligible because it's very small in comparison to the total value. Then we have the diode. The contribution is higher, but is not the main part of this value. And then we have the inductor. Here we have our main problem. The inductor shows the highest contribution to the total size. And finally, we have the capacitor, which in practice is the total size of 5 capacitors connected in parallel, as we explained in the design steps. And as you can see, the contribution is very small. So, as a conclusion for this first buck converter design, our main problem in terms of losses is the diode and the conduction. And our main problem in terms of size is the inductor, which is the main contribution to the final value. So our target for future videos is to show you different designs, different approaches to improve both parameters, the power losses, especially the diode power losses, and the size. So thank you for watching these videos and see you